Hi, my name is Julia O'Malley. Welcome to my video. I decided to focus more on a statistical probability theory route for my project, and I'll be using calculus techniques and applications to prove the central limit theorem. Enjoy! Early versions of the central limit theorem were introduced and first proven by a man named Abraham de Moivre in 1733. Further developments were made in the 19th century when mathematicians and statisticians like Pierre-Simon de Laplace and Semyon Denis came together and furthered his calculations. The central limit theorem is a statistical theory that states that given a sufficiently large sample from a population with a finite level of variance, the mean of all samples from the same population will be approximately equal to the mean of the population. Furthermore, all of the samples will follow an approximately normal distribution pattern, with all variances being approximately equal to the variance of the population divided by each sample's size. So ultimately what that definition is saying is that as sample size n increases, the sample mean will approach the value of the population mean, eventually becoming equal. It doesn't matter what the distribution looked like originally. It could be the complete opposite of a normal distribution, or simply not resemble it whatsoever. However, in all scenarios, the sampling distribution of the sample means will eventually become fairly normal. Let's say we have a distribution of numbers representing random numbers put in a bag. We'll have numbers 1 through 6. And let's say we have 1 1 in there, 2 2s, 0 3s, 3 4s, 4 5s, and 4 6s as well. This means that our population size is going to be equal to 14, and we'll make our sample size equal to 5. And this just means that there'll be 5 numbers in each sample. I took the mean prior to the video and I got 4.36. And that's the mean of the population. So now we can take each sample, and let's say for sample 1 we got a 2, 4, 5, 6, 6. For sample 2, we pulled out a 4, 4, 2 5s, and a 6. Sample 3, we got a 2, 4, and 3 5s. For sample 4, we got a 1, 2, 5, 5, and a 6. And then for sample 5, we got a 1, 4, 4, and 2 6s. Now we can take the mean of each of these samples. So for sample mean 1, we get a 4.6. Sample mean 2, we end up getting a 4.8. The mean for sample 3 is a 4.2. Sample mean 4 is 3.8. And finally, sample mean 5 is 4.2. So now we can take the mean of all the means and we can compare it to the population mean to see if it's anywhere near it. And in fact, we get 4.32. And that reassures one of the main points in the definition that the sample mean is just about equal to the population mean. Now I rewrote our means from each sample, and This is just a reminder that our population mean is 4.36 and our sampling distribution of our samples mean is 4.32. So now we can start to graph the means and create our actual sampling distribution. We know the middle of the graph is going to be around 4.3, so we can label that there. Then we can start to plot the points. We have a 4.6, 4.8, 4.2, 3.8, and another 4.2. You can start to see the normal curve forming. Now this is just when the sample size n is equal to 5. However, as essential limit theorem definition states, the bigger sample size n gets, the more the curve will look normal. If n was equal to 30 or maybe even 40, the sampling distribution of the sample means becomes a more dramatic normal curve. Another way to describe the normal curve that we will attain by the end of this example is the limit of many independent coin flips. With any given coin, there is an original probability that heads will show up half the time, while tails will show up the other half. This makes our probability of flipping a head equal to 0.5 and our expected x value equal to 1/2. If I were to toss the coin twice, the probability it will land on heads is still 0.5. However, since there's 2 tosses, my expected value x equals 1. With 4 tosses, the probability of heads is yet again 0.5, but the expected value x increases to 2. This process continues as the amount of tosses increases. For this proof, we're going to consider 30 samples of 100 coin flips. Now, coin flipping is one of my very few talents, and I took this opportunity to embrace it and showcase it. So I did every single one of these coin flips. So here's some behind the scenes action. Heads. Tails. 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 Here I have a list of each of my samples' means. Each time I finished one round of 100 flips, I calculated the mean and repeated that 30 times. I also put them in order so it'd be easier to plot. So now that we have our list of means, we can find the mean of the means. Once calculated out, our overall mean here turns out to be 50.2. Our expected value is 50, so that compares nicely. Now we can make our sampling distribution of the sample means. The mean is 50.2, and we can start to plot each number. So we have 37, 38, 42, 42, 43, 44, 58, 59, 60, 62, and 68. And after 3,000 long coin flips, it is clear that our sampling distribution of the sample means is in fact normal. Here I have the full proof of the central limit theorem. I'm not going to go into full detail, but I'll mention the main steps taken. This proof is based around characteristic functions. We start with a basic characteristic function formula, then use the Taylor series to expand it out. Algebra comes in handy next and is used to manipulate the equations. We move to defining formulas used to find the sample means and variances, and after all those calculations, We combine them and eventually come to the conclusion of both the standardized mean and the sample mean having a limit that equals a normal curve.